one here? I don't know, is there someone sitting there? No. Okay, so I continue with the practical unit. Yeah. So yeah, again, an overview of what am I about to cover. So I will give you some really quick basics again on raster and vector data. And we will focus on some practical tasks that you usually encounter when you use remote sensing data. First is, how can I get access to remote sensing data? How can I download it? Then how can I handle remote sensing data? For instance, some pre-processing, first view it, some raster manipulation. So basically everything to extract, or not everything, some points, to extract information from remote sensing data. And then we have two big blocks. So basically, I wanted to go to one line from download to some product. So basically, the data we generated before or downloaded, we will use to for a classification task. And as a last part or last slot, I will go a bit into vegetation phenology, because these are some things I encountered when reading some of the literature, so that I thought that might be interesting for you guys. Okay, let's start with the basics. So basically it's also a bit of a repetition of what Martina says. So raster data, so remote sensing usually comes in raster format. A raster is a georeference data set that is composed of a matrix or grid of cells covering a given extent, and each pixel is usually associated to a particular coordinate, and each pixel has usually a certain value which can represent a phenomenon or an attribute. It can be a categorical value, for instance, in case of categorical land cover classification, like you have urban, a pixel is urban, or a pixel is some vegetation, but it can also be a continuous measurement. For instance, in the case of raw remote sensing data, surface reflections, that's usually a continuous measurement. Yeah, again, the smaller the pixel size, the higher the resolution of an image. So meaning the more or the smaller the pixels, the more you can see in the image. And there are usually different formats you can get access to. Raster data, for example, I'm not sure, but we are using mostly TIFF, or I think a relatively new format, JPEG 2000 in the Geo version. You also have the GRIS or ASCII, so there are different formats you can use or download raster data. The second data we will use, I'm not going super into detail here, because we just we'll just include some of the vector data just to give you some basic concept. So you have 3 types of data, points, lines, and polygons. A point is usually like a single coordinate. A line is just usually composed of at least two points and the segment in between. And a polygon is composed of at least 3 points and covers the area between the tree, or the hull between the points. For vector data, for each point, line segment, or polygon, you usually have also some attributes. Normally, it's each feature in a vector data set has an ID, and then each feature, of course, has some coordinates. Either for the points, it's only the coordinate for 1 point. For the line, it's for the 2 points, and for the polygon, for the endpoints you use to construct this polygon. And then, of course, you can also have attributes. For instance, I don't know, you have, let's say you have a polygon that covers some field area or some houses, so you can have an ID for the houses and stuff like that. Okay. And of course, there are also different formats to work with vector data. So the most common ones I encounter are GeoPackage, and shapefile. Shapefile is a bit more tricky to handle, because a shapefile is usually composed of different files. So you don't have only the shapefile, but you also have to have the CRS file that gives you the coordinates. You have the database and stuff like that. So GeoPackage is usually easier to handle, and I tend to use GeoPackage. So. And yeah, the library, oh, I forgot before to say it, the library to handle raster data is Terra, which is a further development of a former package, but it's from the same developer that was called raster. So we will use mainly this, and for the vector data, it's SF, but I think you have encountered that with the code you've seen on the previous days. Yeah, okay, let's go to data acquisition. So as I mentioned earlier, the majority of remote sensing data comes from publicly funded space missions. So the data is openly accessible, it's free of charge, and it's somehow publicly distributed. There are different ways you can get this data. For instance, as a mission providers, as I said before, ESA or NASA as an example, at official data and service providers. One example would be in the US, USGS, or in Europe, the Copernicus data space system. That's basically stuff I focused on, the Copernicus data space system. But you can also go for commercial platforms for Earth science. Famous examples are Google Earth Engine, and some I learned the day before was the Microsoft Planetary Computer, which I don't know, as I figured, I'm really new to this, so it's a bit same in the functionalities as Google Earth Engine. Okay, as I said, we focus on official data and service providers. So what do you need to get access to that data? First, you need an account. Usually they have a website and you have to register yourself with an email address and a password and give some personal information, maybe some information where you are working, what you're using the data for, scientific purpose, commercial purpose, whatever. And then there are two common ways to download the data. So one is if you're using a GUI. So basically all of these providers usually have a website where they have the GUI, where you can, I don't know, access all the site dates, like, hey, the extent which you want to download, the dates range you want to download, and the data sets. And then you basically just need a compatible browser to use it. But yeah, I think today it's not a problem because I haven't encountered any problems there. So if using a web API backend, you need a programming language that can access that service, for instance, R or Python. The other thing you need is clarity on what data or product you are looking for. I mean, like what kind of satellite data you are looking for. I don't know, there are, as I said, different missions, different data sets, also different levels. Please make sure you download level 2 and higher, because the other ones you don't want to use. Yeah, you need to have an idea about the spatial, temporal extent of your data, and of course enough free disk space on your computer to just download or store the data and then to process, because just storing is one thing, but I often encounter problems. I don't know if I work on a personal computer to process the data, because processing then increases the disk space, and then I don't know, at some point you run into problems. And of course you need a geospatial software to view the data and process, depending on what you want to do with it. Okay. So let's first go to the Copernicus Dataspace website. I mentioned that before, this official data provider. So I made an AniMove kind of email address and password where you can access the data. And we're going to download I'm going to show you how to download one particular tile using a GUI first. I wrote here, please don't download the data, because I have already downloaded the tile we want to process for you, but I just wanted to show you. So basically we go on this website. Where's my mouse? There. And we first register. Okay. And then you can go, if you just want to download the data, you go on Explore the data. Yes?
We are not seeing your screen.
Oh, okay. How can I change that? I don't know.
just a projection. I think it's projecting only the PowerPoint.
Okay. It's a bit weird. Ah, because I'm in presentation mode. Okay, sorry. Okay, so I logged in, and now if I want to browse the data, I go to Explore Data and Data Collections. So here we have different data we can download, but I would say we download first like one data set, and of course they are focused as it's a European mission on Sentinel. So we want to go for Sentinel-2 because that's their multispectral mission. And then you go to the Explorer. Or did I go wrong? Ah, here. Sorry, it was wrong. To the Copernicus browser we go. And yeah, then we have here some, we go on that search button. We specify the data we want to search for at Sentinel. And then you can specify the level. So as I said before, we want to have level 2A because that's already preprocessed in the sense that's corrected for the effects of the atmosphere. You can here specify the cloud coverage with this slider. I don't know, I said something in the presentation on how much clouds we will allow. So 15% cloud cover. So that's very restrictive. Okay, and then we have to specify the date, and I specified just one date. It's basically the 13th of June in 2023. This you can do here. And okay, that didn't work.
Ines, I have a quick question.
Yeah.
And this, I just might have missed this, but is the Sentinel, I guess if you're, is that what you would, the sensor you'd want to choose if you're, focusing on the European region?
No, I checked that you can download it for the whole world there. I was also not sure whether Copernicus just provides for the European Union, but we also use an API later, and I tested it here as well, and you can also download the data from worldwide.
Oh, cool.
So, yeah.
Cool, thanks.
So that worked properly with the big screen. I don't know if I'm doing something wrong here. Okay, sorry, I had some problems defining the date. So there you define the date, and then you usually don't want to download the data for the whole world. So you want to specify an area of interest. So you can either draw just a rectangle, you can draw a polygon, or you can just upload some data, and that's what I'm going to do. It has to be in GeoJSON format, and I prepared a data set from Mögging and some area around here, basically. So if you also want to do that data set is also in your data folder. It's basically the AOE data space GeoJSON. And as you see here, we are now at the area somewhere here. So we specified the date, we specified the satellite, and we specified the area of interest, we specified the cloud cover, and now we can just click on search. and wait. So, and yeah, then what you see here, it's showing 50 results of 72. So for that area of interest that I chose, there are basically 50 different, different images or tiles available. So I'm interested. Okay, I think sorry. I think there's still something wrong with the dates. Yeah. Okay, so if you just look for the 1 day, the results are reducing. So we see here 4 images basically in our that are somehow overlapping with the ROE we are interested in. And I think I would download that one, or I have downloaded that one, so please don't download it. But what you can do, you can visualize it here if you click the visualize button, so you see the actual data you would download. You can also, as I said before, do already the color compositing, just for visualization purposes, of course. You can look at some indices, NDVI, just to get some first grab of the data you're downloading. Then you, here in that field, you have some information button that gives you some idea about the product. So here we are collecting Sentinel-2. It's Sentinel-2B, so it's the second Sentinel of the two sensor constellation. Yeah, you get some information about the product. The process that it was processed by ESA, for instance, the relative orbit number and the path number and all that stuff. Okay, and what you would do now is basically just click on that download button to download the whole file. And yeah, as I said, don't download because I downloaded that already for you, and you find the data set here in the Sentinel-2A in your data folder. Okay. So let me quickly go back to the presentation. So that's, yeah, sorry.
Sorry, I have a question here. So do you only download one of these files because it doesn't completely cover your
Yeah, you
area?
download just tiles. So here, if you would want to cover the whole thing, you probably would have to download multiple images. It just gives you the overlap basically, but you download a complete tile. Also, if you have, if the tile doesn't cover your whole area of interest, you download the whole tile. But I thought we were starting with this. But there are also options to download just data, also already from multiple tiles to for one ROE. But that's not what you can do with the GUI. But that's something we do later with the API.
Cool. Thank you.
So the file is already stored. I was interested, it's already stored in your data folder. Yeah, usually when you download the data, you want to look at the documentation. So I don't know, to understand like what bands are covered, what spectral range, what's the resolution, if there are any problems and stuff like this. And you could, sorry. I gave you a link. I don't know, I had to find a bit of a workaround because I couldn't include a link of a PowerPoint, of a PDF. So here you have the link to the PDF. It's a really long document. Oh no, it's not. It's 40 pages. So here you... So here you see some product specifications, and that's something you want to, I don't know, look at, for instance, in the beginning. Anyway, I don't know. So let's do our first hands-on. So now after we have downloaded the tile of data, we want to get a look at the data. So that would be the first R script I'm tackling today. It's a 010 RS data Sentinel-2 get a first glimpse. Yeah. I've included R project link. That's probably easier if you open the R project, because then the links should work properly. Yeah. Is this bigger? Yeah.
Can everyone see the text in our studio from the back? Is it okay? Should it be bigger?
It's okay.
Okay.
Okay. Yeah. So that's basically what you want to do. We have downloaded the tile, so we want to get a first glimpse at the data. So what we use for this is the Terra package. And what we needed to do is to unzip the file, because the file is coming zipped, and yeah, that's basically just doing the unzipping. Okay, now we have unzipped the file, and now we can look actually at what we get when we download one tile of data. So the actual data is basically covered in that granule folder. And you have again some name code. And then you have three folders. Like one is giving you auxiliary data. One is giving you the image data. That's actually where the different images or the different images taken in the different spectral ranges are stored in. So for instance, here in the 10-meter sections, you have band 1, 2, 3, 4, and 5. And you have some additional layers. I actually don't know. This is the water vapor layer and some other information that you can use as quality input.
So
and
when we open our project, do we need to set a working directory?
I don't think so, because if you have it all in one folder, I don't know, like I was setting it up like having an AniMove folder, then the scripts in one folder, the data in one folder. So if you open the project, it should work.
What should the working directory be?
I think I'm not sure that people have a project Ines, so that's the.
Okay, so the working directory then depends. It's where the scripts are in the scripts file folder. No, it's not the data folder. It's the folder where you have your scripts.
The working directory should be the folder with the script.
Yeah.
And it will reference the data folder automatically.
Yeah, if you
That's what I thought, but I'm getting an error.
I put it to the data and it works when I put working directory to the data.
Okay.
Yeah, some people can't find the data. Like, can you show in the folders, like which folder?
Okay. Maybe to fix the problem, I don't know. Does anyone still have the problem? Because yeah, I think what I did is I put my scripts in a scripts folder, which is now here named AniMove 24 scripts, and I put all the data I gave you on the USB sticks in a data folder. And these should be both together in an overall folder. And when you have this lineup, you can just open the R project file in the scripts folder, and then all the links should work.
No, for me I had to put the data inside scripts, only then it works. Like the data folder inside scripts, and then it works.
Okay. Okay, but then you didn't, yeah. I don't know, I have it like this. Yeah. Okay. Okay. Okay, I'm really sorry that took a while. Yeah, basically, I don't know if it works for all of you. I know for some of you it doesn't work, but anyway, I will explain it now and maybe run code through, line through the code. And you can use it afterwards, or I help you fix it during the lunch break, because otherwise we can't go on. So what I wanted to say, or what we did now, basically, if the script was working, was unzipping the downloaded file with the tiles, and what you do get is a bunch of data. I go back again. Okay, so here in the Sentinel, so you have the zip file, and here you have the unzipped file, and that's basically everything you get from one tile, and in the granule is your actual data. You have the image data from the different sensors in the different resolution with 10 meter and the single bands, 10 meter, 20 meter, and so on, and some extra information. And what you also get is a quality index layer that basically gives you some information on snow probability, for instance here, or on cloud probability, and also for the different spatial resolutions. So there's a bunch of data. There's also a metadata file. It's an HTML. It's a bit tough to read. It gives you an overview of what you find in the different folder, what is the offset, and stuff like that, the solar irradiance. So basically some bunch of extra information. What we want to do now is we want to view the files first. So this basically gives you a list of the files that we want to look at, and we are only interested in the 10 meter resolution. So here you get a list with only the 10 meter resolution files, and we update the band names a bit, and what we then do is we create a virtual raster. Well, this doesn't create a virtual raster, but that's the file name to the virtual raster. And here we build a virtual raster for these bands, using the VRT. So a virtual raster is basically you have the raster layers in the single bands already laid somewhere in your folder, and you don't want to physically load them into your disk space or into your R environment. So you build a virtual raster, which is basically a text file I can show you that has the links to the different bands in the data and works as if it is a raster. So R can display it as a raster. You can do calculations on it, but without physically loading it into your R environment. So we have now created that file, and we will now load that file. Maybe I can show you what we created to give you an idea. That's in the folder, I'm sorry. So here's the VRT page. You can easily open that file with the text editor. And what you see here is basically it's just a bunch of references to the different band. For instance, here is band 2, here's band 1, band 3, band 4, and it only works so when you create such a raster, you cannot just copy the file, the text file, the VRT file, because as soon as the references or the links to the data are different, it won't work. Okay, so in R, this data basically works as if it is a raster. So we have loaded that VRT file, and we can now get by clicking on the name of the variable R, we can now get some information on the raster itself. So it says it's a class spot raster. That's basically the class of the Terra package. You get some information about the dimensions of the raster, the number of rows, columns, and layers. So basically here we have like roughly 100 times 100 kilometer coverage of that tile. And we have 4 color layers, and these layers are the different bands we looked at in the 10 times 10 meter. Here you get the geographically coverage, you get the information which coordinate reference system your data is in, the data source on your disk space, and the names of the single bands. They are now not really named in a proper way. They are just like basically derived from the band names. What you can now do is plot the selected bands, these 4 bands side by side, by using the plot operation. So this is just like a way to view the different files. As far as I remember, it is like in the 10 meter resolution, you have red, blue, green, and near. This is most likely near because here you have the reflectance, the high reflectance of the vegetation, and the other 3 are basically red, green, and blue. And what you also see, this on the bottom right is some cloud cover that's still there. Okay, this is one way of plotting the images side by side, but you can also plot just one image, and that you can do by indexing. So indexing basically gives you which, so the layers are collected in a stack. It gives you like which kind of layer you want to plot. In this case, we want to plot the first, or want to get information about the first stack of layers. So here you can also plot or look at the different layers, not by indexing by number, but by the names. So here I plotted the names, which are really not good right now, but anyway, it gives you some band 1, band 2, band 3, band 4, and then you can index with that band named as a character and also get the information. So now we want to plot the first or the third layer in the image stack. That's what we can do also with the plot function, R, and indexing the number 3. So it gives you a plot of the third layer instead of plotting it all. You can also plot the image already, as I said before, as a color composite. I used here for this you can use the plot RGB function in Terra, for instance. So you have to specify the raster you're interested in, and you have to specify the bands. So the bands basically give you which band, if you want to plot an RGB image, like how we see the world, you have to specify R. So band 3 is red, band 2 is green on green, and band 1 is blue on the blue position. And you usually do a stretch. So the stretch basically you usually have, like, if you have super bright spots, like cloud, for instance, your value range is really high. So you have some of the values really low, and then you have all of a sudden super high cloud values. So what you do is you stretch the image values between like a lower range, and to exclude the outsiders, for instance, between the first and the 99th percentile, so to let you see. So here you can also already plot some information about the value range. What you see here, this function only uses 1% of the cells. So it plots the distribution of the cell values for 1% of the cells in the raster. You can also extract the cell values of the raster. So basically that gives you a vector of all values included within the first raster layer. So, for instance, here we can now inspect what kind of value range we have. So the maximum value is 19,600, and the minimum value is 1. So you have a value range between 1 and 19,600. And now you can also plot this val vector and see the whole distribution of the value range in the raster. So basically that's just like something you do at first. You want to look at the value ranges, you want to, I don't know, plot your image, inspect your single image files, and that's just to get a first glimpse on the data. Yeah.
Are we looking out for anything in particular with the value ranges?
Sometimes you want to see whether you have some outliers, for instance. I don't know. It's just a way of plotting, actually, I used here. So sometimes you need to extract the values to do some further calculations. This is one way to do it, but then you extract all the values. But here it's just like, because I showed you the histogram function, which works on the raster layer, but only includes 1% of the raster layer values. And if you're not sure, for instance, for the stretch, if there is a value out of the normal range, you could use this and get the minimum and maximum values. It's just for inspection. It's not anything particular.
And so, sorry, I'm a little bit confused here. So we have the different bands that we would ideally work on all of this collectively. Is that the plan?
No, that's not what you're doing. So usually you decide which bands you want to use. So a good way to start is often the RGB. Then, for instance, you're interested in vegetation, then you would, of course, use the NER band. So here I just wanted to show you some plotting. So we just focused on the 10-meter resolution. We have 4 bands in 10-meter resolution, which are red, blue, green, and the near. And we put them together in a raster stack, an image stack that's called. And then we use that image stack to create some plots, to, I don't know, just get a first view of the data. Yeah.
Okay.
Does it help a bit?
Yes, I think so. And then from this, we will just work with one of those bands, or
we will work with this is just inspection. This is nothing to do with what comes after. Yeah.
Okay, sure. Thank you.
So when you apply the stretch function to, is it just for visualization,
It's
or
just for visualization.
it doesn't change the underlying value?
No.
Okay.
No. It's just for visualization purpose. Okay, so that was just like how to get a first glimpse on your data. And maybe the second, let me go back to my presentation. Okay, so the second part you want to do is some pre-processing. I named that remote sensing data handling. So common pre-processing task would be to create a stack of images. We did that with a virtual raster already, I don't know, in a simplified way. But here we want to really combine these bands together and create a physical layer containing the different band layers. So this requires the band layers to have the same coordinate system. I mean, here it's not a big problem because we use bands from one tile, so they are obviously so they obviously have the same dimensions. We need the same extent and we need the same resolution pixel size. That's really important because, for instance, in Sentinel we have the 20-meter and 10-meter resolution, and you cannot stack them in one band because they have different resolution, but we will, I don't know, find a workaround to do that anyway. What you also want to do, we have the level 2 data. It's already atmospherically corrected. Maybe that's something I should mention here because somebody asked me if atmospheric correction removes the cloud. It does not remove the cloud. The clouds are there anyway. It just removes the effect of the atmosphere. For instance, the images are really hazy when you look at the level 1C data without atmospheric correction, and this haze comes from all the scattering and stuff, and that's corrected in the atmospheric corrections. Clouds are opaque, they are still there, so you want to get rid of them. So basically what we do here is we will mask pixels that are contamined by clouds because you don't want to include them in your data. And you can also exclude the snow. Sometimes snow is also a problem. You don't want to have snow pixels in your data or in your analysis, so you can also remove them. This requires you to generate a cloud mask. Usually you have some information layers with all the layers you get with your data package, and from that you can create the cloud mask. So basically that's also something we want to do. And what you also want to do, that's basically tackling some of the questions you have. You have like an AOI, like an area of interest that covers your species range or whatever, or something you want to look at, and you want to bring you want to generate an image that covers the whole the area you are actually interested. That can involve stacking or mosaicing the tiles, basically putting multiple tiles together in one, so that you have one continuous image, or it can mean, and that's what we are going to do today, to crop your image to a smaller extent, because then it has less it uses less data space and it's easier to process. And the third one is like data inspection. I told you before, we can view satellite images. We already seen the true color images in different images, and we can also plot some false color images. So that's also something, if you want to say, like, hey, I'm interested in vegetation. How can I see vegetation? Is vegetation a particular, or is there a particular feature I'm looking for? Then I can use these false color combinations to look if I can see the features in the data. So that's basically the pre-processing, and that's the next script I've prepared. RS data handling Sentinel-2. I would also suggest I go through the script line by line, and I close the presentation. Okay. So prepare, download Sentinel image for further processing. That's basically some pre-processing. So the goal of the script is to create an image stack containing 10 bands with 10-meter resolution. Remember, just by default, we only have 4 bands with 10-meter resolution. So we want to, somehow change the resolution of the other images. We want to mask cloud and snow pixels. We want to crop the stack to the ROD extent. We want to reproject the stack in another coordinate system, because that's also something you want to do from time to time. And we want to plot some color composites. So first I load the libraries. It's Terra, FF, tidyterra. It's for plotting, map tiles for plotting, ggplot for plotting, and RS2balls also for plotting. Yes.
Thank you. So you mentioned that we need to reproject. So the files that we are normally getting are projected for that specific area, and we need to reproject them so we can do.
You don't need to, but sometimes you want to. For instance, these we got are in World Geographic VGS 8432N, and sometimes you want to project them. For instance, if you work, I had that occasion, I worked in Europe, and I had different tiles covering mostly the European continent. And if you use VGS projected coordinates, you have different zones. And that causes some problems when you want to mosaic them together. So I projected it in a European-wide coordinate system to get it more even, so it was easier with the handling, basically. And sometimes you want to do that, so I just show you how it works. Yeah.
So they are always coming in the projection of what they were created for the specific tile, correct?
I'm not sure if they were created in that, but they are coming in a specific coordinate system. It's probably also mentioned in the data documentation file. Yeah.
Sorry, one quick question. Does it matter the order of doing first the mosaic and then cutting for the area of interest, or doing the opposite way? That's not.
What do you mean, like ordering? If I do reprojecting and then
like first creating the mosaic of like if we have, for example, the 4 tiles, creating the mosaic and then
the reprojecting. In that case, I would do it before, because when you mosaic them, you get problems when you cannot mosaic them when they are in a different coordinate system. So in that case, it's that way around. I do it now after I stacked and crop, because then the data is is smaller and it doesn't take so long to project. So it's case by case basis, basically. But I will tell you, I don't know, if you want to stack something or mosaic something that doesn't fit together, I will tell you. Yeah. So we create an image stack of bands with inches with 10-meter resolution. That's what we want to do. So we first, what we want to load are the bands in 10-meter resolution. So blue, green, and red are these three. We load the near band. We load the three red edge bands that are in 20-meter resolution, and we want to have the narrow near band that's in it's also in 20-meter resolution, and the two shortwave infrared bands. So I basically just made up a list of these bands. So then we list these files in with the 10 and 20-meter resolution in the things. In the folder, so basically that goes into the data folder where we have all our images stored, and we look for certain images in these, for all images, or we try to list all images with 10 and 20-meter resolution in this Sentinel-2 folder. So then we loop through the bands that I specified before, and we download that bands using that band, or we just just want to not have all the 20 and 10-meter resolution bands, but only the ones that are listed here. So basically, this is just selecting the proper bands. And here you now have a list of 10 images or 10 bands that are the ones that I specified in the beginning. Okay, and as I said before, we cannot work together with 10-meter and 20-meter resolution. So if we want to create the stack, we need to do something to match the resolutions. So that's why so this separates the 10-meter and 20-meter resolution bands. And what we can now do, we build a stack as we did before for the 10-meter and 20-meter resolution bands using a virtual raster. So what we can do here, so I wouldn't suggest you to run it, but I've prepared I just go quickly through the code. So now we have two images, the bands with 10-meter spatial resolution are 10, and the bands with 20-meter resolution. And now we want to concatenate them, meaning stack in one data layer. So let's try to run that. Error, so Rust number of rows or columns does not match. So basically that's the problem. We cannot combine them if they are not in the same resolution. And what we want to do is called resampling. So we want to resample the 20-meter resolution using this function, the 20-meter resolution bands to the resolution of the 10-meter resolution using the method near. Let me quickly give you an overview what resampling does in the practical. So with resampling, you basically, this is resampling and reprojection. As soon as you when you reproject your raster, you shift it a bit, so the original values of the raster are not anymore in the position where they should be, so you need to do something. In our case, we want to change the resolution from 20 meter to 10 meters, so we have to cut the raster. And for that, you usually do some resampling. And yes?
But how can you go from a lower resolution to a higher resolution? It's
just mathematically. It's not, the measurements stay the same. These bands have been recorded with 20-meter resolution. It's just you create a new raster that's having 10-meter resolution, but basically having the same information from the 10-meter bands.
So you're not gaining more detail, or you're
just
dividing?
No, you don't get any more detail.
Pixel.
You get the same detail. For instance, if you want to, yeah?
Sorry, I didn't mean to interrupt you. I just wanted to ask, then why would you not make the finer resolution one more coarse?
because then I lose the finer detail from these bands, which can help later, for instance, to. So if I increase the resolution of the 20-meter bands, I mean, I get the same as the 20-meter bands. It's basically the same. I just can combine it with the 10-meter bands and do some calculations. If I would resample, that's also an option, the 10-meter resolution up to 20-meter, I would lose the spectral detail because I would somehow create a merged value from 4 pixels that were basically individual pixel measurements. It's just for let's just say we want to combine data with different resolution. We don't get more detail. It's just like the data structure changes and it's not 20 meter but 10 meters now. And what you do basically, you shift your data or you split your data, you single pixels. In that case, like you halve them, so you get 4 pixels out of 1 before. And you usually, the new value in your pixels will be derived from the neighboring pixels. In that case, from the four pixels beside you, and you have different values, different methods. So you can either use the value of the nearest cell. That's really important because that doesn't change your values at all of the raster. So basically it just shifts the location, properly the location of your pixel value, but it doesn't change the values at all. So for instance, in that case, you would maybe use the pixel value of this in your new reprojected or resampled raster. You can also use the values of the 4 nearest cell to calculate a new value, to interpolate that value. For instance, you would take the 4 values around your pixel and then calculate the mean to associate a value in the middle of that pixel in that new raster. That would change your intensity. Okay, let's go back to the thing. So here I chose the method near because I wanted to, I want to resample the 20-meter data down to 10 meter, and I choose the method near because I want to keep the original values. That's basically why I do that. Okay, then I can, like when I have resampled that, I just told you do not run because it takes some time. I can now stack the 10-meter and 10-meter fake 20-meter resolution together in one image. And I wrote that image here in the data folder. And we can load it now as a stack here. And when we now look at the stack, at the information, so we see that all the cells have the same spatial resolution now. Okay, now we have created that stack with 10 images of our original image tile. And what we want to do is next is we want to check for clouds. So usually the images or the tiles you download come with some quality index layer. So when you go in the granule folder, you don't need to do it. I just showed you. So here it's the QE data. And you get some information about clouds and other stuff, saturation and blah, blah, blah. So here I will use, for Sentinel-2, you have a particular layer, that's the cloud probability layer at 20-meter spatial resolution. So we will use this to inspect clouds. So we load that data, and then we can plot it. Then what you see here is basically the probability that your pixel is somehow contamined by clouds. So low values, dark values are probably clear pixels, and bright values here in yellow and greenish color have a higher probability of a cloud, to be a cloud. Yes.
Can I quickly ask, can snow cover be conflated with cloud cover in this probability matrix?
No, in that case, you have a cloud probability mask too. But that's Sentinel specific. So usually, I don't know, for Landsat data, for instance, you have a quality layer band that's encoded that has like per pixel super long integers. And on each bit of the integer is some information encoded. For instance, bit 1 is like the cloud, yes or no, it's Boolean, yes or no cloud. Then you have snow and stuff like that. So you have to retrieve the information somehow. Yeah. Okay, let's plot the image again from the stack in RGB. And what we see, as I showed you before, so here you see the clouds, and these clouds are also here in the cloud probability mask.
Will it be the same case if we're going to use the level 1C to have a mask for the cirrus clouds?
Yeah, I mean, the cloud mask is usually a byproduct you get when you do the atmospheric correction. So level 1C hasn't done any atmospheric correction. You would have seen the cloud, yes, but you wouldn't have any information layers like this probability mask to mask the clouds.
So with this, we can also get rid of the cirrus clouds.
I mean, this is just cloud probability. I think sometimes, I don't know, like this doesn't have, it depends on your data. So sometimes you have cirrus encoded, sometimes you only have clouds. I think this is just cloud, and I think there is no cirrus in that case. But for instance, with, as I told you before, the Landsat band, the quality layer, the information that's encoded on the different bits of this long integer value you get per pixel, there's also one for zeros. So it's always a bit of looking, hey, I want to remove clouds, so, and then get the information out of these layers, produce yourself a mask, and then mask the stuff you want to get rid of. Yeah. Okay, so again, we need to resample the cloud mask because the cloud mask is in 20-meter resolution, and remember we resampled our stack, so it's in 10-meter resolution. So in order to associate the pixels that are cloud with the pixels that are cloud in our 10-meter resolution stack, we need to resample it. I quickly do it here. I hope it doesn't take that long. Yeah, that's quite quick, I hope. So here you get a verbose. And yeah, now we create a cloud mask from our data. So here you see the probability. Usually you have to decide on a threshold. There is no one way, like, hey, 20 is, I don't know, I want to get rid of 20. Like if there is a pixel that is has a cloud probability of 20%, I want to exclude it. It depends on whatever like application task you have. In that case, I chose just 60% just for demonstration. And this is the cloud mask, which I generate with the if-else function in the Terra package. So basically, it says like if my cloud mask or my cloud probability layer has a probability layer a higher probability than 60% of being a cloud, then put in an A. Otherwise, put a 1. So basically, that should work quite quickly. So what we get then is a mask that has 1 everywhere where there's no cloud and an NA value where there is no cloud. And that's basically the format you need to mask the clouds using the mask function in Terra. The mask function, then we want to, like now we have created that cloud mask, so we want to use that cloud mask to mask the pixels that are NA in that cloud mask in our layer stack. So we run this. Okay, maybe we don't run that. I have created it already, so let's not do it. We can load that and the mask stack, so we can plot 1 layer in the stack that is now masked or not masked. So you still see the clouds here on the bottom, and then we load the stack with the mask clouds, the same layer. And you can see they are just removed. They are just NA values now, and you won't be a problem for your calculations. Okay, I'm not sure. Shall we continue a bit or? Okay. So the next step or the next task I would yeah.
So basically, you are just creating NAs to not have that information for the calculations. But
yeah, I think you can also do it differently. So that's with this mask function.
With the mask function.
Thing. You can also create, I also created ones like ones and zeros. So I asked for like probability of cloud larger than 60% zero, and so that became a zero. And if there was a low probability of being a cloud, it became a 1. And then you can also multiply it with your data. But for the mask function in Terra, you would need the clouds to be NA and the valid data to be 1. So that's what I did it. Yeah.
And there's no kind of a way to approximate values in those areas that are empty. For example, if the area of interest is turns out that there's a lot of clouds.
There are some people who do some interpolation based on, I don't know, the surroundings, but that's a science for itself. I wouldn't go for it because you basically falsify that. I don't know, would require you to have us be in a really homogeneous area, because otherwise you get values of, I don't know, different objects. I wouldn't do it.
So you will need rather different years that same place to see if we can get the cover.
the problem we always have, also when you look at a multi-temporal perspective, so I said we have an optimal resolution, for instance, for Landsat for one satellite of 16 days. Of course, you get a measurement every 16 days, but you cannot use the measurement every 16 days because depending on which area you are, you will have images that are fully covered with cloud. This is a really good image because you only have, I don't know, we decided on it, we only have 15% cloud cover. So you can basically use 85% of the data. But I don't know, so if you look at a time series, you will never get, or rarely, I mean, maybe there are some regions on Earth where cloud cover is low, so, but you won't get any multi-temporal information that's regular. You won't usually have some gaps and stuff like that. So clouds are a problem. So, yeah.
Now, I just wanted to say, you can also create a mosaic from, if you need like one photo per month, for example, you can create a mosaic and combine the areas without the cloud cover.
That's not something you call mosaic, because mosaic is basically the same day and you just combine different tiles. So here we have just one tile. You combine the tiles to cover a larger area. So you have multiple tiles to cover them together. If this is one day, and if you want to have, I don't know, different tiles for a different area or different mosaics for a different time, then you, of course, have images from another time, have another mosaic. And then you have, again, images for another and have another mosaic. So it's, I don't know, it's like this. So you depend on the measurements. You won't get like multi-temporal measurements every time. So it can be that your second, while you were lucky in the first mosaic and got all the clear view images, and the second mosaic, it can be that 3 images are not useful. You cannot use them because they are covered by cloud. So you just have the multi-temporal information at that time for one tile, let's say. Yeah.
I think the question was if you don't need like every 15 minutes data, every 15 days data, but you need once a month, if you could like combine like from the 2 measurements tiles or something. Was that more like the...
Sorry,
so,
I don't understand.
Yeah, no, it's
I'm
okay.
really sorry. Yeah, okay, if you're looking for a month perspective, you can use all the measurements from the months and combine them in an aggregated layer that gives you information for the months, but it does not necessarily be that one tile is from the same date as the other tile. It just gives you an aggregation over the month. I'm really sorry, I understood that wrong.
But would you then average? So if you have like 2 tiles without clouds?
You can also average, yeah. I mean, it depends what you want to do. If you want to use NDVI, if you have only one image, for instance, you only use that value of that one image. But if you have 5 images, for instance, for another tile, you can average. You can calculate the mean or whatever, max, yeah. Yeah. Okay, what we do next is to crop our data, as said before. So this is the whole tile, and we are basically interested in a smaller area. That area is here. I also saved that as a geo package on the folder. which first checks the projection. It's the same projection. No, it's not the same projection. Yeah, it's a different projection. So here we have the EPSG code, which gives you the coordinate reference system for the tile. It's VGS32N, I told you before. And the ROE is in a different projection in EPSG 432026, which is basically the one that I told you before that you can use for whole Europe. So what we need to do first, and that's answering the question when you do projections, when you need it. In that case, we need it. We project the ROE from the original CRS to the CRS of the stack. And now we have the same, so we also have our AOI in the VGS32N. So what we do next is we get a footprint of the stack of the CRM. That's just for plotting purposes. So I want to know the exact footprint of my stack. And then I plot it. Exactly. So this gives you the footprint of the tile. So this is the tile we downloaded. And this is the area we are basically interested in. So what we want to do is we want to only keep the information that's in here. I mean, it's not completely covered. I told you that before because, I don't know, we have only one image. We downloaded one image, and to cover the whole thing, we probably would need another image, but I skipped that. So what we want to do is we want to crop it to that extent, the stack. And that's what you do with the function crop. You take the stack with the removed clouds, and you use the projected ROE, and then the function crop basically crops the information of the stack to that new extent. And then we can plot it again. ggRGB is basically a plotting function. I told you before I had the plot for the RGB plot done using the Terra function. This is a function that's implemented in the RS Toolbox package. It works basically the same. You also give an image stack, then you define the bands you want to combine to plot the RGB, and you define the stretch. And here, in that case, in that particular function, you have to say that it's the geometric raster. And on top of that, we will plot the AOI. So our new image, basically, what we have now created with the cropping function is just like covering the extent. Sorry. It's just covering the extent of the, of that AOI. Yeah.
If I understand what we just did, we cropped the image to the AOI.
Yeah.
But it looks like there's a little mismatch. Is that like a projection mismatch?
Projection failure, yeah. Okay. And also, I don't know, the AOI may not, so you can only crop image bands full pixel. You cannot have half pixels.
Okay.
So you will always have some kind of overlap if you use a vector data set or like a vector shapefile to crop the data.
It's like edge pixels.
Yeah.
Okay.
But they are not like I'm really sorry. These are not half pixels, so you always have full pixels. You will never cut an image and have like only 5 meter, half 5 meter pixel in the edge. Yeah.
Okay, thank you.
Okay, so this is just an AOI we used to crop our image, but sometimes you also have, I don't know, some extra data, for instance, your trajectories, your movement trajectories, and you want to know the extent of your movement trajectories. So this would be an alternative for cropping where you don't already have an AOI. So I have created that trajectory. I have to transform it into the CRS of my image stack. That's not the cropped one, it's the stacked one, because I want to show you a different version, how you can do it. And now we can plot, what we can do to or what I can do to show you what I want to do is to plot the the tile on top of the OSM image. So here you have the OSM image, and here you have a fake trajectory that would go this direction. It's a similar extent as we have with the AOI, but we just don't have an AOI, so to say. So what we can do now is with this STB box function, we can create a bounding box that's covering this trajectory, and we can convert it to an vector data set, and this vector data set we can now plot again on top. This didn't work. Tile not found. Oh, sorry, I changed the name. It's OSM tile, sorry, I changed the name. So, I'm really sorry. So here you see that would be your bounding box we just created for covering the extent of your movement trajectory. And what we can now do is we use this bounding box and also crop our extent. I think it's quick, so we can just run it. And then we can plot it. So now we have the image also cropped like we did before, but this time to the bounding box. Of course, this trajectory also is bigger than the image, the tile extent, but we have cropped it to the similar extent with another method. Okay, now we want to reproject the stack in a new coordinate system. I told you before this is VGS 84, so let's assume we are somewhere in Europe, we're covering a big area, and we don't want to use VGS in 32N and different zones, so we want to project it in another coordinate system. And so that's basically what you do with the project function in Terra. So the project function takes your raster layer, and in the Y, it takes your information on the coordinate reference system you want to project your raster in. Okay. So I create the CRS. So that's the CRS new is basically the new coordinate reference systems here in EPSG code 3035, which is the ETRS 89 extended. So that's the coordinate reference system, which basically covers whole Europe. Yeah, so now I can project it. So it takes some time, so I'm not doing it. And here again, like with resampling, I have to identify a resampling method that's used when, like, I don't know, maybe I'm going quickly back to the presentation. So when you project your raster, you will shift it. That's basically this case. Somehow it will be shifted. So you have to define also, again, a resampling method telling you how to redistribute or reassign the new pixel values of the new raster in reference to the old raster. Okay. So I wouldn't run it because it really takes some time, but we can load the reprojected raster again. And we can check the coordinate reference system, and now we see that the reprojected raster, after we would have run that function, would be 3035. And the last part we would do for preprocessing, or not, it's not really preprocessing, it's just data inspection. If you want to look at your data you've created a bit more in detail, you can plot these color composites. You can just plot an RGB image, as we can see here, but you can also plot the different false color composites. For that, I would just give some. Let me quickly show. So I just want to give the different bands a more intuitive name. So basically here I gsub the bands file to just include whether it's band 2, which resolution it has and stuff. And in this function, I assign the band names. I just create the file of band names to the different layers in that raster stacks. So originally the names in the raster stacks are Sentinel, 10 meter 1, blah, blah, blah. And now, after we applied this function, so we have more intuitive band names. Okay, let's do some plotting. I gave you a link here to a webpage with Sentinel-2 band names in the format we just saved, and also with some common band combinations you can use to create false color composites. For instance, so here you, I don't know, see the different band combinations or images. You see the bands, and here's some common band combinations. So this is natural color, RGB. That's the color infrared with the near, so used for vegetation monitoring. Shortwave infrared, I don't know, there are many bands with many different application areas. Depends on what you are searching for. You can look for these band combinations to highlight your data. And what you do here, we just plot a true color composite or an RGB image. That's basically how we see the world. And a false color composite would be plotted, for instance, with for the vegetation monitoring by switching the band positions. So, for instance, here the red band is on the blue position, and on the red position we have the near band. And then we can just plot that. And you get, this more reddish image where the vegetation is highlighted in red and non-vegetated areas are highlighted in, this turquoise something, and water is black. Okay, that would be, I have something else. It's just basically plotting, putting different information. So on the RGB, so here on 10 you have the shortwave infrared, on 4, on green you have the near infrared, on blue you have the red and the blue. So this looks different. This is also for agricultural monitoring, and it gives you not just highlighting of vegetation, but also vegetation conditions, with darker areas being healthier vegetation than lighter areas. Yeah, you can also plot the raster, an ROE, and the AniMove location using the RS toolbox functionalities. For instance, here we have to transform our AOI to the same coordinate system, 30, 35. We projected our data in. Then I prepared the AniMove location. It has the same coordinate system as our data, so we can just plot it also on top of each other. So here you have some, opportunities how you can plot different things just to inspect the data. Okay. Yeah.
How do I, if I want to plot another place, let's say, you plotted where it's the AniMove now, but if I want to play somewhere else, how do I, find this place?
You mean the coordinates?
Yes, because there is this AniMove PKG.
Yeah, I
location?
created that by looking, and so I did it in QGIS, really stupid. So I just created a point layer. I showed you the different formats of the vector laser. I just created a point layer and put that point on top of that building. So that's like how I do it. You can also, if you look for other locations, you can also do it here in R. For instance, Google Maps, I think, gives you the coordinates, and then you can create an image or a point layer based on the coordinates. I can show you that maybe next week if you're interested in that. Yeah.
Thank you.
Yeah. Okay, that was basically that for the some of the pre-processing tasks. Of course, it's not exhaustive, so it depends on what data you download. You might have different tasks, but these are one of the common ones I often use, so I thought they might be interesting for you. I'm not sure. It smells a bit like food. If we should go for the break or... Okay.